In this video, we're going to look at a couple different practice problems for differentiability. First one, we're going to consider a piecewise function, f of x equals 0 when x is less than or equal to 0, and it's going to be x squared when x is greater than 0. So let's draw this function first. So this function is going to be 0, the constant function 0, when x is less than or equal to 0, and it's going to be x squared when x is greater than 0. So note that this function is continuous everywhere. For a piecewise function, we need that each piece is continuous and they have to match up at the right point. And in this case, it does match up. All right, but is this function differentiable everywhere? The only possible issue is at 0. So we'll say issue with a question mark, because we're not really sure if it is an issue. What we're going to need to do is we need to check the one-sided limits to see if they agree. So the first, let's check the left limit, the limit as h approaches 0 from the left of f of 0 plus h minus f of 0 over h. That's what's happening to the derivatives, the slopes, as we move to 0 from the left. And in that case, that's just going to be 0 because the slope of a constant function is 0 always. So from the left, we have 0. And from the right, we look at our limit. We think about what's happening to the slopes as we move to the right. Well, these slopes are getting smaller and smaller, and they're actually approaching 0 in a much different way than they're doing from the left, but they're still approaching 0. We can think about if we have the function just x squared, what happens at 0? We have a horizontal tangent line, which means that we have a slope of 0 at that point. So because these agree, then that means that the limit itself without the left and right is going to be the same value, which is 0, which is a finite number, which means the derivative exists. So is the function differentiable everywhere? Yes, it is. It is continuous and differentiable. Now let's think about the derivative. Is that differentiable everywhere? And we're going to need to draw the derivative. So note that we know the derivative of 0 is going to be 0 always. And we've learned in a previous video that the derivative of x squared is 2x. And if you don't believe me on that, go through the limit definition of the derivative to verify that the derivative of x squared is 2x. At this point, we're just going to use that as a fact, and we will learn it formally in the next couple chapters or next couple sections. Either way, this is the derivative here. And if we sketch this, we have on the left, we have just the constant function 0. And on the right, we have the function 2x. So here, this is continuous everywhere. But we have a corner here, which means that it is not differentiable at x equals 0. If you think about the left and the right-hand limits, the left limit will be 0, just as we had before. The right limit is going to be 2, as the slope of the tangent line is 2, always for that function 2x. So is f prime differentiable everywhere? The answer is no. So now let's think about the second derivative. Second derivative is piecewise, and we know that it's going to be 0 if x is less than 0, and it's going to be 2. The derivative of 2x is 2. It's the slope of the line if x is greater than 0. And note that I no longer have less than or equal to because the derivative doesn't exist at that point 0. So I can't actually put that in the second derivative. So what does this look like? We have, on the left, we have this 0 function, and on the right, we have the constant function 2. So this function is now not continuous at x equals 0, and it is also not differentiable then at x equals 0. And there is a relationship between everything we have here. The biggest one is when we went from not differentiable at x equals 0 for the first derivative to not continuous at x equals 0 for the derivative. That is what's going on, because that's what differentiable means in some cases, is that if something is not differentiable, it means its derivative is not continuous at that point. And then we know if it's not continuous, it can't be differentiable. All right, the other example we're going to do is very quick. We have, is f of x equals x to the negative 2 differentiable everywhere? So in a previous video, we showed with the limit definition of the derivative that the derivative of x to the negative 2 is negative 2 over x cubed. And you can use the limit definition of the derivative to show that again if you need to. So the question is this function differentiable everywhere? And we know that f prime of x is not continuous at x equals 0 because there are domain issues. You can't plug 0 into the denominator. So because the derivative is not continuous at x equals 0, then the function is not differentiable at x equals 0. So the answer to this question is no. It is not differentiable everywhere. It's not differentiable at x equals 0.